Hello friends, in today's video we will learn about the Brillouin zones and we will try to construct the Brillouin zones in 1 dimension and 2 dimension. So in the previous unit we have already studied about Brillouin zone and we have defined Brillouin zones in a variety of ways. In this unit we will be assuming a Brillouin zone as a representation of permissive values of K in the K space. So in the previous chapter, we defined the Brillouin zone as a set of points in reciprocal space that are closer to the origin than to any other lattice point. There are plenty of definitions, and in the K space, the Brillouin zone can also be defined as the permissive values of K. And with this assumption, let us consider a one-dimensional linear lattice and let us plot the Brillouin zone in that case. So we have already analyzed the electron motion in a one-dimensional periodic lattice. We have seen that the energy spectrum of an electron moving through a periodic lattice is not continuous, but consists of allowed and forbidden bands. And at what values exactly these discontinuities in energies happen? As we have already seen, these discontinuities happen when the right hand side of the previously defined function, which is cos Ka, equal to plus or minus 1. When this limit was exceeded by the other function, we got discontinuities in energies. So cos Ka equal to plus or minus 1 implies Ka equal to plus or minus n pi, which implies K equal to plus or minus n pi by A. So at these values of K, we have discontinuities in energies, and these K values are not permitted for an electron moving within a crystal. So as you can see, here the n values are different integer values 1, 2, 3 and so on. If the K value, the wave vector value of an electron are these values, then a small increase in electron momentum will increase the energy of the electron so that it can jump discontinuously from the top of one allowed band to the bottom of the next band. Similarly, if you look into this different K values plotted here, you can see the K values are permitted in the range minus pi by A to plus pi by A, and at these values of K minus pi by A and plus pi by A, the first boundary is seen. So the region between minus pi by A and plus pi by A and those values of permitted K values constitute the first Brillouin zone. And after that, at these points, these values of K minus pi by A and plus pi by a discontinuity in K is observed, and these discontinuity values of K are the boundaries of the first Brillouin zone. Then after that, from pi by A to 2 pi by A, all the K values are permitted, but the value of 2 pi by A, there is a discontinuity. Similarly, at minus 2 pi by A, there is another discontinuity. So in between those values from minus pi by A to minus 2 pi by A and plus pi by A to plus 2 pi by A, those regions constitute the second Brillouin zone, and those are the second permitted values of K. Similarly, there are third Brillouin zone as well as fourth Brillouin zone and so on. So these values of K where discontinuities are seen are the boundaries of the Brillouin zone in the one-dimensional case. Now moving on to the case of a two-dimensional lattice. For simplicity, we will be assuming a square lattice. Now we have seen in the previous class about Bragg's law. We define Bragg's law in a variety of ways, and one form of Bragg's law is given by 2 into K bar dot G bar equal to mod G square. It can also be defined as 2 into K bar dot G bar plus G square equal to 0. Both these equations are one and same. Now similar to an X-ray diffraction, when X-rays fall on the crystal lattice, if they satisfy the Bragg's condition, they will get diffracted. Similar to the X-ray diffraction, the electrons which are also moving like a wave within a crystal can get diffracted if the Bragg's condition is satisfied by them. We know the electrons have different k values depending on their wave vector value, and if their wave vector is in such a way that the Bragg's condition is satisfied, the electron moving within a lattice will get diffracted. And those values of k bar are not permitted for electrons because it cannot propagate through the crystal with that value of k. It will be getting diffracted due to Bragg's diffraction, and only the other values of k's are permitted which are not satisfying the Bragg's condition. So as we can see, certain k values are clearly prohibited by the Bragg's condition for the electron. If the electron choose that k value, it will be undergoing Bragg's diffraction and not able to propagate through the crystal. So let us assume the Bragg's condition to find which all values of k bar are prohibited, and hence in that way we will have a beautiful explanation for the Bragg's explanation for the Brillouin zone. So because Brillouin zones are the regions with permitted k values. So if we can find which all k values are not permitted, we can clearly construct the boundaries of the Brillouin zones. So in the case of a two-dimensional square lattice, as we have already seen, the direct translation vectors are a bar equal to a I cap and b bar equal to b j cap. A and b are same for a square lattice, and if we construct the reciprocal lattice vectors, it is given by a star is 2 pi by a I cap and b star is 2 pi by a j cap, and with these reciprocal lattice vectors, the basic vectors, we can construct the reciprocal lattice vector translation vector g bar as n1 a star plus n2 b star. So it will be n1 into 2 pi by a I cap plus n2 into 2 pi by a j cap. So it will be simply 2 pi by a into n1 I cap plus n2 j cap. So this is the translation vector in the reciprocal lattice. Now the k bar, the wave vector k bar of the electrons can be simply defined as k bar equal to kx I cap plus ky j cap, where the kx and ky are the x component and y component of the wave vector of the electron. Now substituting k bar and g bar into the Bragg's condition, 2 into k bar dot g bar equal to mod g square, it is given by 2 into 2 pi by a into n1 I cap plus n2 j cap dot kx I cap plus ky j cap equal to mod g square. So mod g square is simply g bar dot g bar. So it is 2 pi by a into n1 I cap plus n2 j cap dot 2 pi by a into n1 I cap plus n2 j cap. So find the dot product. You can find this dot product to be equal to, the left hand side is simply 4 pi by a into n1 kx plus n2 ky. 4 pi by a into n1 kx plus n2 ky. The right hand side is 4 pi square by a square into n1 square plus n2 square. It is simply n1 into n1 plus n2 into n2. So it is 4 pi square by a square into n1 square plus n2 square. Cancelling the common terms, we can obtain n1 kx plus n2 ky equal to pi by a into n1 square plus n2 square. So this is the simplified form of the Bragg's condition within a crystal in the case of electrons. Here kx and ky are the wave vector components along the x direction and y direction of the electron. N1 and N2 are integers. Now, whenever this condition is satisfied, the electron wave function cannot exist because electrons will be diffracted and it cannot propagate. So, what is the minimum values that we can choose? The first set of values can be N1 equal to plus or minus 1 and N2 equal to 0. This will give the most basic equation where the Bragg's condition will be satisfied. So, what is the answer? What is the solution? It means simply plus or minus kx equal to pi by a or kx equal to plus or minus pi by a. So, this is the first value where the Bragg's diffraction will be happening, and hence these values of kx are not permitted for the electron waves within a crystal. Similarly, the next values N1 equal to 0 and N2 equal to plus or minus 1, N1 equal to 0 and N2 equal to plus or minus 1 will yield you ky equal to plus or minus pi by a. So, these are the first boundaries of k values or the boundaries of the first Brillouin zone. So, if you plot the reciprocal space kx along the x-axis and ky along the y-axis, the first boundaries are seen at kx equal to pi by a. So, as indicated here, this straight line corresponds to kx equal to pi by a, and this straight line corresponds to kx equal to minus pi by a. Then ky equal to pi by a. This straight line corresponds to ky equal to pi by a, and ky equal to minus pi by a is the bottom line. So, these boundary values are not permitted for electrons because they will be scattered, they will be diffracted according to the Bragg's law, and within these values all k values are permitted. So, this region will form the boundary of the first Brillouin zone for a two-dimensional square lattice. Now, that is we have four straight lines. Kx equal to plus or minus pi by are two parallel lines. Ky equal to plus or minus pi by are other two sets of parallel lines, and these square region will constitute the first Brillouin zone. Now, how to calculate the second Brillouin zone? Second Brillouin zone will be the next region or next set of allowed k values. So, for that, choose N1 and N2 in the next range. So, next possible value is N1 equal to plus or minus 1 and N2 equal to plus or minus 1. So, let us take each of the cases. First, let us choose N1 equal to 1, N2 equal to 1. So, this implies kx plus ky equal to 2 pi by a. Then there is the next condition, N1 equal to minus 1, N2 equal to 1 plus 1, and this condition will yield us minus kx plus ky equal to 2 pi by a. Similarly, choose the next combination, N1 equal to 1, N2 equal to minus 1 will yield kx minus ky equal to 2 pi by a, and choosing both values as negative, we will obtain minus kx minus ky equal to 2 pi by a. So, these four straight lines are the next boundaries or the next combinations of k values not permitted. So, what are those straight lines? Here, this curve, this straight line here, this is the curve corresponding to kx plus ky equal to 2 pi by a. Similarly, there are other curves with other conditions, minus kx plus ky or minus kx minus ky and kx minus ky. These four straight lines can be plotted. These four straight lines 1, 2, 3 and 4 can be plotted as these diagonal curves, diagonal straight lines, and the region bounded by these regions, excluding the first region, first Brillouin zone, is the second Brillouin zone. So as you can see, this region here, this region, and this region constitute the second Brillouin zone. In a similar manner, you can choose and find the other Brillouin zones by choosing different combinations of N1 and N2. So if electrons are moving with these values of K, where this condition, if any of these values of K values are chosen by electron moving within a crystal, it will be diffracted and it cannot propagate through the crystal. So these conditions can yield us the shape of the Brillouin zones in the two-dimensional case. So I hope this portion is clear for you. In this portion, we have assumed the condition for existence of an electron wave function, and we have defined the Brillouin zone as the permissive values of K. So we were able to plot the Brillouin zone in the one-dimensional case because we know certain K values are not allowed. Similarly, based on the Bragg's diffraction condition, we also tried to plot the Brillouin zones in the two-dimensional case. I hope this portion is clear for you. Thank you.